Okay, so last time we talked about different intermolecular forces that hold molecules together in different condensed phases particularly. We talked a little bit about the properties of liquids, although there's not much more to say with those. But today we're going to start talking about solids, which is a state of matter where we're going to have a lot to say about in the next few lectures that we'll have. Okay, so as we get started, let's first define the different types of solids that there are. So we can sort of categorize them in two big categories, and then within those categories there's some subcategories that we'll potentially think about. So amorphous solids, which we won't deal with a whole lot, but they are one important category, are solids that have no regular structure. So in this case, the atoms or the molecules that make up the solid, they're sort of randomly arranged in space. There's no regularity to it. We can't easily predict where the next atom or ion is going to be in that solid. So everything is random, and because there's really the absence of structure here, there's not much more we can say about it. We can't classify the structures of amorphous compounds very well because they more or less have no regularly defined structures. Okay, so the atoms and molecules are arranged randomly. The classic example of this, which is one you've certainly seen in everyday life, is glass. Okay? So glass is an example of amorphous solid. It's usually made out of SiO2, silicon dioxide, which is molten, and then when they cool it down, it forms a solid, but that solid, even though it has regular composition, does not have a regular structure to it. The other big category, which is what we're going to spend the most of our time on, are crystalline solids. So these are solids where the components are arranged in a highly regular and periodic fashion. Okay, so in this case, we have atoms and molecules, which would be the components of these, and the positions of those atoms and molecules are very predictable in a three-dimensional sense. So they're very regular, and by periodic we mean that the structure repeats itself over and over again in all three directions. So no matter which direction we're going in the crystal, we can predict the location of the atoms or the molecules in that structure. So we have to get a few other definitions out of the way first before we talk in detail about crystalline solids. So one is lattice. So if we imagine in a crystalline solid, each of the atoms or molecules that makes up that crystal, we define them as a point in space. So the lattice then is a three-dimensional system of points where each of those points represents an atom or molecule. Okay, so each point represents an atom or molecule in the crystal, and it extends in all three dimensions, all three directions. I suppose an ion could be considered a lattice point as well, as when we talk about ionic compounds starting next week. Alright, so for lattices, that's sort of how we think about crystals. They're a three-dimensional array of points, and each point represents an atom or molecule or ion. Now to simplify things a little bit, because lattices are infinite, a lattice extends in all three directions out to infinity, we can define a simpler unit called the unit cell, and this is the smallest repeating unit in the crystal. And more specifically, it's the smallest unit which can be generated by translating, it's the smallest unit where we can generate the lattice by translating it in all three directions. So we take our unit cell, we translate it in the x, y, and z directions, and that generates the lattice. So the lattice is generated by translating the unit cell in all three directions. Alright, and as we'll see in this section, the unit cell is usually a pretty simple geometric shape. We'll be almost exclusively talking about cubic shapes. And then we take those cubes, those small cubes of atoms, and we move them around, we translate them in all three directions, and that's going to generate our infinite lattice in the crystal. Now within crystalline solids there are three main types, and we'll talk in some level of detail about all of these. The first two especially we'll talk about a lot, and those are atomic and ionic solids. So atomic solids, as the name suggests, only consist of one type of atom. So they're all elemental, they're all elements, there's no compounds in this case, just a single element. So an atomic solid is made up of one type of atom, but those atoms are arranged in a very regular, repeating three-dimensional unit, as we call it, as for all crystalline solids. So there are some examples which we'll talk about in more detail. So diamond, which is made up of carbon, and the carbon atoms in diamond are arranged in very regular fashion, as I show. This picture up here is a small piece of a diamond structure. And then most metals that we'll talk about also are atomic solids. So there's one type of metal atom in the structure, and those atoms are arranged in space in a very regular three-dimensional pattern. The other type that we'll talk a lot about starting next week are ionic solids. Now we already know from earlier in the course a lot about ionic compounds and various properties of them and things of that sort. Now we're going to actually talk about their structure. In ionic solids, the lattice points are made up of the positive and negative ions. So each position in our lattice is occupied by an ion, and those are going to be arranged in a regular repeating fashion. We know a lot of examples of ionic compounds, so I'll just give you a few. And we're going to talk about in detail the structures of many of these. So we've talked sodium chloride, that's a very simple structure type that we'll get into next week. Zinc sulfide is another one, magnesium chloride, and so on. Okay, so there's a lot of different ionic compounds, and typically in the crystalline phase, in the solid state, their structures are this type of ionic solid, where we have repeating combinations of ions. And then finally, the last one, which we won't deal with a lot, but does relate back to what we talked about last week, last lecture, are molecular solids. So in this case, they're covalent compounds, so they're molecular compounds, which means they're made up of nonmetals, of some combination of two or more nonmetals in this case. And the lattice points are the molecules themselves. Now what holds those molecules together in the structure, that's what we learned about last time, those intermolecular forces. So in a molecular solid, the molecules are held together by intermolecular forces. So it's going to be some combination of London dispersion forces, dipole-dipole interactions, or hydrogen bonds that are going to hold those molecules together into a very regular pattern. And the classic example of this is ice. So if you lived in a colder climate for any part of your life, you definitely would have seen snowflakes before, and they have those nice hexagonal shapes because the water molecules arrange themselves in a very regular hexagonal pattern that gives rise to those unique shapes. And then in the case of ice, which I picture up here at the top of this column here, you have the water molecules that are held together by hydrogen bonding interactions in all three directions. Alright, so that's what keeps it in sort of this regular three-dimensional array, but it's individual molecules, and the only thing holding them together are intermolecular forces, not any type of bond or ion-ion interaction, as is the case in other compounds. Now, before we start talking about structures of crystalline solids, we want to understand how do we experimentally determine the structure. This is actually a very important technique, one that I just used this morning here at UH, so it's, even in modern days, it's still widely used and is the best technique we have for determining the structures of crystalline solids. And so that's called Xray diffraction. And so as the name implies, we have our X-ray beam. So we have an X-ray beam here, which is going to be directed onto a crystal, this little cube here. and then the beam comes off the crystal, it's diffracted in all different directions. Okay, so this is an application of diffraction. We talked about diffraction a little bit earlier in the course, probably in chapter 2 or 3 when we started introducing the properties of waves. So diffraction is a property of waves, where when it when it strikes a regular array of points, it's going to scatter off in all different directions. In this case, the regular array of points are the atoms in the crystal. So for X-ray diffraction, the X-rays hit the crystal and they scatter off of the atoms. And then two different things can happen. So as the X-rays come off the crystal, the individual waves, the individual photons can either be in phase or out of phase. So if the two phases line up, you get constructive interference. And then if the two waves are out of phase, where the peak of one wave is overlaid with the trough of another wave, you get destructive interference and it cancels out. So essentially what we're doing here at the detector, all of our diffracted X-ray beams go and they strike a photographic film, and that's where we're going to detect the diffracted X-rays. So the spots that we see on the plate, those represent where the X-rays constructively interfere. Okay, so everywhere where there's constructive interference, we're going to have X-ray intensity coming off, and that's going to strike the plate in these different positions, and then we then see spots where each of those diffracted X-ray beams strikes the crystal. Now the mathematical basis behind X-ray diffraction and what allows us to determine the structures using this technique is called Bragg's law. So in Bragg's law, what we need to know are a few parameters here. Alright, so one is we need the wavelength of the X-ray beams, lambda. Okay, so we talked about wavelength a long time ago also, and that represents the wavelength of any electromagnetic radiation. And so for this Bragg's law, we need the wavelength of the X-rays we're using. Most X-ray diffraction experiments use X-rays that have wavelengths of about 0.7 angstroms, which is 0.7 times 10 to the minus 10 meters. So a very small wavelength, but that's required because in order for diffraction to occur, the wavelength of the electromagnetic radiation needs to be similar in size to the distance between the things that are doing the scattering. So the distance between atoms in a structure is roughly on the order of angstroms. So if we use a wavelength of X-rays that has about that same value, that's what allows us to observe diffraction and get a lot of meaningful information out of this. So then Bragg's equation depends on two parameters of our X-ray experiment. One of those is the wavelength, as I said, and the other one is theta, which is the angle of incidence with respect to the crystal. So we're going to send the X-ray beams in at some angle, and they're going to deflect at that same angle. And a key component then of this experiment is what we do is we rotate the crystal, or we rotate the X-ray beam, and we change this value in a very systematic fashion. And then where we're going to see constructive interference is when this condition is met. So if this distance here, d, between the two planes is just right, we're going to see constructive interference. So theta is the angle of incidence, which we change throughout the experiment. And then d here is the distance between planes of atoms. So in a crystal we have very regular arrays of atoms, as we talked about. So those atoms are going to form different planes that we can define, and those planes are going to be regularly repeating in space. And so you're going to have a distance between those, which we define as d. And so this equation here, the Bragg equation, which was a father-son duo named Bragg, they spent their quality time deriving the equation for X-ray diffraction, and it goes n lambda is equal to 2d sine theta, where n is an integer. So basically what we're doing in this experiment is we're varying theta and then figuring out at which angles theta does the constructive interference occur. And then once we know those angles and we know the wavelength that we're using, which is defined by the type of X-ray we're using, we can then back out a distance, and that distance allows us to define positions where all the atoms are, and then we can piece together the structure using that information. So the mathematics is way more complicated than this for actually determining the identity of each atom or determining the positions of all of the atoms, but for a simple two-dimensional case like I show you here, this is the Bragg equation, and this is what we sort of want to be familiar with conceptually. I don't think we'll be using this equation in any of the problems, but we should be aware of what it means and that really this is the basis for how we determine structures. Now before we go in and dive in and start talking in detail about the structures of metals, we want to talk about how our metal atoms actually held together chemically. So you might be wondering, we talked in the last lecture about how a lot of atomic elements, like the noble gases in particular, they have very weak intermolecular forces because in that case it's just London dispersion forces. Those are the weakest intermolecular forces, and that's why most of our noble gases and many of our nonmetals exist as gases. So the noble gases, even the heaviest one, is a gas at room temperature, and a lot of our nonmetals like F2, Cl2, O2, those are all gases because you just have those weak forces. But then why are metals, which are also just made up of single atoms, why do those usually exist as solids? And that is because of metallic bonding. So as we talked about way back when, metals, the key characteristic of metals is that their outer electrons are held very loosely. Okay, so they have very loosely held valence electrons that leads to their very easy ionization, which is why they tend to form ionic compounds in combination with nonmetals. So this all relates to that because we now have very loosely held electrons. So instead of thinking of metallic compounds as being arrangements of individual atoms, what we can think about is that all of those ions are loosely held. So we can have an arrangement of positive charges where the valence electrons are then lost. But we haven't completely ionized the molecules yet, but instead those valence electrons are loosely held. So for group 1A, we can imagine they have one valence electron, so there's an array of +1 charges. And then in this, what I'm going to draw here is sort of a smear of yellow, is all those valence electrons are delocalized around all of the atoms. So the valence electrons are not held in place on one atom or another, they're delocalized over the entire structure, and they're responsible for holding those positively charged nuclei relatively close to each other in a condensed phase. Now if we go to group 2A, the other main group metals, so that would be magnesium, calcium, all of those, here we have two loosely held valence electrons, so we can imagine these as being 2+ charges. So again, those loosely held valence electrons, and so we can approximate this structure as being 2+ ions, all arranged in a regular array, but they're being held together by the loosely held valence electrons, which again all represented by sort of a smear of electron density. So it's a very delocalized model where the electrons are free to move around the structure and they're responsible for holding all of these nuclei together. So we're maximizing the attraction by having these electrons shared amongst all the different atoms as opposed to being localized in one or the other. So just to clarify this diagram again, this yellow smear that I've drawn is what we call the sea of electrons. And the key point for all metals is that the valence electrons are loosely held and they're all delocalized. Alright, and so that's how we think about metallic bonding. Bonds do not exist between just two atoms, but there is a delocalized set of valence electrons that hold a lot of atoms together all in the vicinity. So because of this type of bonding that metals exhibit, there's some key properties that we want to understand. So for all of the types of solids that we're going to talk about in this course, we're going to define some key macroscopic properties that relate to their bonding and to their structure. So for metals, let's first characterize their phase changes. So the melting point, which is the point at which they go from solid to liquid, those tend to be moderate to high. Alright, so we have those sea of electrons that's holding all the atoms in place. So in order to liquefy them, which requires us to break some of those interactions, it requires a decent amount of thermal energy. Although we should keep in mind that the melting point, when we melt a metal, we're not completely separating the atoms. The atoms are still in contact with each other, although they're in a much more loosely held arrangement. So we're still able to maintain those attractions between the ions and the sea of electrons. So even in the liquid phase, we have pretty strong interactions between the metals, so we can still melt them at relatively low temperatures. It doesn't require a lot of thermal energy to break down some of those attractions and go from a solid to a liquid. Now, how do the melting points vary across the periodic table? So as we go across the period, in particular from group 1A to group 2A, the melting point increases. Alright, and this is because, especially in the context of main group metals, group 1A and group 2A, as we go across the period from group 1 to group 2, we have higher charges, as I showed above in this diagram up here. Group 1A we can think of as being +1 charges, group 2A are +2 charges. And then because of that higher charge, there's a stronger attraction to the electron sea, which holds them together in a tighter arrangement. It makes it harder to melt the solid into the liquid. Alright. And then as we move down a group, so as we go from the top to the bottom of the periodic table, within a given column of metals, the melting point decreases. So it's the opposite trend. And the reason for that is because we have larger metal ions. As we go, remember the trend for atomic radius, as we go down a group, the atomic radius increases. So if we have a larger metal ions or larger atomic radius, that leads to a weaker attraction to the electron sea. So we talked about in the context of lattice energies that the force of attraction between ions, between charges, depends on the size and depends on the charge and the size or the distance between them. So in this case, if we go down the periodic table, we have larger metal ions. The positive charge is more diffuse. There's a weaker attraction to the electron sea. So the heavier metals actually have lower melting points in most cases. Now the boiling points of metals are very high. Okay, because if we're boiling something, remember we're taking it into the gas phase. And to take metal atoms into the gas phase, we have to completely break all of the forces of attraction between the nuclei and the sea of electrons. So this requires a lot of thermal energy to do this, and so it's very difficult for the cations and the valence electrons to completely separate themselves from the rest. Okay, so those loosely held valence electrons and the cation the nucleus are associated with have to break away from the rest of the atoms, and that's very difficult to do because of those forces of attraction. Okay, so it's not terribly difficult to go from solid to liquid, but to go into the gas phase for metals is very hard because you have to break all of the attractions between them. Now the other properties we'll talk about beyond just the phase change properties are mechanical properties and the electrical and thermal conductivity. So when we talk about mechanical properties, we're talking about how hard it is to break or bend something. So what happens when you exert a force on that material. So mechanical properties, we can define those for all the different types of solids, and those are also related to the structure of them and to the type of bonding that's holding them together. So the key mechanical property of metals is that they're malleable. And malleable is just a synonym for bendable. Okay, so if you think about, if you ever witness a car accident, hopefully not, but if you ever have, or been in one yourself, the metal parts in your car, they don't shatter. Even under very high forces, they bend and they distort, but they don't shatter. So that's what we mean by being malleable. You can bend them, but it's very difficult to completely break or shatter them. And the reason for this malleability in metals is related to the metallic bonding. So the metal ions, even though there's pretty strong attractions keeping them in a condensed phase, they're not held tightly in place because you have that sort of loose amorphous sea of electrons that's holding them together. So the metal ions are not held tightly in place, and they're able to slide through the electron sea without really, breaking any of those attractions too much. Right, because the electrons are so diffuse, the structure can distort very easily, and you don't have to have you're not going to necessarily break all of those forces of attraction by distorting the structure. Now, the other key piece is electrical and thermal conductivity. Especially electrical conductivity is particularly related to the bonding in metals. Right, so electrical conductivity is the ability to conduct electricity, and metals are very good at this because of those loosely held electrons. Particularly in the solid state, where those electrons are pretty mobile, and they're shared between all the different atoms. So there's, again, delocalized electrons is the key here. And that's because the electrons are mobile. Alright, so now we have a good idea of the bonding and the properties of metals. Let's now actually go in and start talking about in detail their crystal structures. So as we go in and talk about crystal structures, we need to first learn how to count atoms in a structure. So mostly what we're going to be doing here is we're going to be talking about cubic unit cells. So we're going to have a cube with atoms arranged at various positions on the cube that are going to define our structure. And we have to be able to know how do we count the atoms in these cubes. So the first possibility is if we have our cube, if we have an atom that's completely in the center of our cube, that's called a body center position. So we can put an atom at the middle of our cube, and in this case, the atom is not shared by more than one cube. So remember that in the lattice, we're going to take these individual cubes, and we're going to stack them in all three directions. All three directions here. But if we have an atom in the center of the cube, it's only held by that one cube. It's not shared by any other unit cell. So an atom in the center of a cube counts as one whole atom. But we can also have then a face center. So our cube has 6 faces that we can put atoms in the center of. So if we have an atom in the center of a face, this face is shared by 2 cubes. As I have it drawn here, it's going to be this cube and the one directly to the left of it. And that atom is going to be shared by those 2 adjoining faces. Okay, so a face center atom is shared by 2 unit cells. So for the purpose of counting atoms in that unit cell, it counts as half of an atom. Alright, another possibility is putting the atoms on the edge. So each cube has 12 edges we can put atoms onto. In this situation, it's a little bit harder to picture, but we have this edge is going to be shared by the cube that's directly to the left of it, and we have 2 cubes directly in front of those 2 that are also sharing that edge position. So each edge is shared by 4 unit cells. So if you have an atom located on the edge, that's going to count as 1/4 of an atom. Okay, so an atom on the edge counts as 1/4, and then finally a very common situation that we'll see is where we have atoms in the corner. So this is edge, and the last one is corner. And here the corner is shared by 8 unit cells. So if you imagine this top face here of the cube, there's 4 other squares that are joined to that it shares a corner with, and then you also have the 4 above that, the 4 cubes above that. So in total, each corner is shared by 8 cubes or 8 unit cells. And so an atom in the corner counts as 1/8. Alright, so that's how we count atoms in the structures. Now let's go ahead and start defining the 3 types of cubic structures. Alright, so the first one is simple cubic. So for these structures, as the name implies, it's the simplest one, and it just represents a cube of atoms where we have each corner has one of those atoms in it. Okay, so it's just a cube. Each corner has a single atom. Now let's think about how we can build these from layers, because it's helpful sometimes to think about how do we generate these three-dimensional structures by taking layers of atoms and stacking them on top of each other. So if we start with a layer that looks like this, where we have a row of atoms all touching each other, and then each successive row is immediately underneath that. So we're going to start with this layer here where all of the atoms are touching. And then we're going to take the next layers and just stack them immediately on top of that. So directly eclipsed on top of the first layer. And that defines a cubic structure where in a layer of atoms we have 4 spheres that touch each other. One, two, three, 4, and then we have the 4 above that, which are going to define then a cube. So you have a simple cube, and there's a few different representations we're going to be familiar with. So this top one here is one representation of the unit cell, which just shows small spheres at each corner. That's probably the most convenient way to represent it. And then this middle one here is a bigger picture of the lattice. So it's taking this small cube and translating it in different directions to get this larger array of points, where the simplest unit within that is the cube, which we then move in all 3 directions to generate the rest. And then this bottom part here, which is sometimes helpful to think about, is that we use sort of the space filling model where we show the full volume occupied by the sphere. So in reality, the atoms are going to arrange themselves until they're touching, until the atomic radii are directly adjacent to each other. And so it's helpful to think about these also where you have this space filling arrangement. So now for each of the structure types, we're going to define some parameters about them. Alright, so what we're going to do in these is we're going to define the length of a side in terms of the atomic radius, and then we're going to classify what's called the packing efficiency at the end, which is the total amount of the total percentage of the space that's occupied by the atoms. So if we go back up to this cubic structure here, we have atoms in each corner, but we also notice that in the middle of our cube there's a lot of empty space. So we're going to try to figure out which arrangement of atoms is the most efficient packing arrangement, which occupies most of the available volume, and we're going to define that for each of these structures. Okay, so for simple cubic, the geometry is pretty simple. So I took geometry a long time ago, back in 1999, so it took a little bit of time for this to come back to me. But we're going to use pretty simple geometric arguments to define different parameters of our structures. So if we look at our one face of our cube here, okay, this is the face of a cube, which we then arrange in 3 dimensions to make our cube. We have, along each side, we have 2 radiuses. So as we go from here to the center of the edge, it's 1 radius. Here to the center is another radius. So the length of the side, which we abbreviate with A, in all of these cubic structures. So cubes, remember from geometry that all the lengths of the sides are equal in the cube. So there's just one side length we have to define, which we call A, and that's equal to 2 times the atomic radius R, where R is the radius of the atom that makes up our structure. So then the volume of our cube, the volume of our unit cell, is equal to A cubed. That's another geometry argument, and then that's going to be equal in terms of radius to 2R cubed, which is 8R cubed. Okay, so the volume in terms of radius is 8R cubed. Now the other thing we want to be able to do for all of these is count the number of atoms in the unit cell, or the number of spheres that make that up. So remember we have 8 corners, each of them has an atom on it. So we have 8 corner atoms. Each of those counts as 1/8, so the corners are shared by 8 unit cells. So that means in net our unit cell has a total of 1 sphere. Now if we go back up here, it's really 8/8 of a sphere, but in total it accounts for 1 sphere in the unit cell, 1 atom. Okay, so our unit cell has 1 atom, and that means the volume of the spheres in the unit cell, we have 1 of them, The volume of a sphere is 4/3 pi r cubed, where r is the radius of that atom. And so that means we have the volume that's occupied by the atoms themselves is 4/3 pi r cubed. So to define a packing efficiency, what we're going to do is we're going to take the volume of those spheres, the volume of the atoms themselves, we're going to divide that by the total available volume in the cube and multiply it by 100. So this is going to tell us what percentage of the cube's volume is actually occupied by the atoms. So the volume of our atoms is 4/3 pi r cubed. There's one of them and it has the volume of 4/3 pi r cubed. We're going to divide that by the volume of the cube, which in terms of r is 8 pi r cubed. Sorry, 8 r cubed, not pi. So the radius cancels out. And so this is going to be equal to 4/3 pi divided by 8, which is still multiplied by 100, which is pi over 6 times 100, which is 52.4% numerically. Okay, so that means in a simple cubic structure, just over 50% of the volume is occupied by atoms. The rest of that, almost 48%, is empty space. Okay, so almost half of our volume here is empty space. We can clearly see it there in the middle of our structure. Now the next structure type we're going to talk about is, let's say we took our simple cube and we put an atom to fill in a lot of that empty space. So we have all this empty space in the center. Let's go ahead and occupy it with another atom. Now the empty space is not quite big enough to fit an entire atom, but the way we can generate a body-centered cubic structure where now we have an atom at the center is we're going to take a layer of atoms with a space between them. So we're going to place all of our atoms in a layer, but we're going to leave some space in between them. Okay, so in order, then we're going to have our second layer, which I'm representing with red spheres just for clarity. This is layer 1, and then layer 2 is going to be placed so that it's over the top of those spaces. We're going to fill in those spaces with the second layer. The second layer is in a metallic structure, the same type of atom, but I'm just showing it in red to sort of highlight it and make it clearer and easier to understand. So we're going to stack our second layer over the spaces in the first layer. And then finally the third layer is going to be placed, it's going to be on top of that second layer, but it's going to be lined up or eclipsing the first layer. So the third layer is going to be stacked so that it eclipses the first. And we're also showing this in blue because it's directly on top of that first layer, or directly over it. Alright, so if we think about this layered structure then, 8 of these blue spheres make up a cube, and then they have one red sphere in the middle that's at the body center. So when we depict this structure, we have a cube of atoms with one more here in the center. The lattice becomes more complicated as we extend that out in 3 dimensions, and in the space filling model, again, we have each corner is occupied by 1/8 of a sphere, 1/8 of an atom, and then we have a single full atom that's in the middle of all of those residing at the center of our cube. Okay, so that's the information about the body-centered structure, and so now let's define some of the parameters for this. Now geometrically this is a little bit more complicated, so it's not that difficult of a structure, it's just a cube with an atom in the middle. To define the geometry is a little bit more complicated. We're not going to ask you to do geometric derivations on the exam, but it is helpful for understanding the structure. So what we're doing here is we're going to take the length of our diagonal from one corner of the cube all the way to the opposite one. That's going to be this red line here. And as we go from along the diagonal from corner to corner, we're going to go through the one atom that's in the corner, which is 1 radius. We're going to go through the atom in the center of our cube, which would be a distance of 2r, twice the radius as we go through this atom. And then finally, to get to the opposite corner, we have another atom in that corner, which is another r. So from simple geometry, the length of a cube diagonal in terms of a, where a is the side length, d squared is going to be a squared plus a squared plus a squared, or 3a squared, which means that the length of this diagonal is a radical 3. So this length here is the face diagonal, a radical 2. This is another one of our edges, a. Okay, so then the length of the diagonal from corner to corner, though, is a radical 3. Which means we want to derive a relationship between the length of the side a and the radius of our sphere r. Our diagonal distance is a radical 3, and as we saw here, that's equal to 4 times the radius, r to r, which means our side length in terms of radius is 4r over radical 3. So for a simple cubic structure, a is equal to twice the radius. For a body-centered cubic structure, it's a little bit bigger than twice the radius. 4 divided by radical 3 is a little bit bigger than 2, and that's because we have to expand out the structure a little bit to be able to fit that atom in the center. Now in terms of counting the number of spheres, the number of atoms per unit cell, we still have our 8 corners, and each of those has 1/8 of an atom that's shared between 8 unit cells. But then we also have our body center. So we have 1 atom at the center. That counts as 1 full atom because it's not shared by any other cube. And so we have a total of 2 atoms in our structure this time. So simple cubic is 1 atom per unit cell. This has 2. And so if we want to get the volume of the spheres now, there's 2 of those spheres. Each of them has a volume of 4/3 pi r cubed. And so the total volume occupied by the atoms, which we represent as spheres, is 8/3 pi r cubed. And then for the packing efficiency, we're going to take this volume here, the volume of the atoms, 8/3 pi r cubed. We're going to divide that by the volume of the cube itself. So here, the cube, the side length in terms of radius, is 4r over radical 3. So the volume of our cube is 4r over radical 3, and that whole quantity is cubed. Alright, so again, the radiuses cancel out, and if we multiply this by 100 and take it numerically, it gives us 68%. Alright, so 68% of our volume is occupied by atoms in this case, so it's much more efficient packing than what we saw in simple cubic, which is only 52%. So we have about 68% of the volume occupied by atoms. The rest of this 32% is empty space. Alright, so in the interest of time, I will stop there. We'll cover face-centered cubic next time, as well as some more details about these structures. So I will see you all next week.